So this video is looking at our last spectroscopy, which is NMR. So it's called Nuclear Magnetic Resonance Spectroscopy. So it's going to be abbreviated NMR. Okay. And what I'm going to do is kind of go through this packet here. You will need some kind of highlighter of some sort to kind of highlight the important bits of information. This packet's pretty heavy on theory, so I just want to kind of glance over some things to kind of give you some background. Draw on the top of your notes here the ester with 4 carbons. I have 1 carbon over here, and then I have 2 carbons on the oxygen end of that ester. So what NMR, it is the premier spectroscopy that organic chemists use. If any of you have had an MRI, it is exactly the same thing. It's called magnetic resonance imaging. They thought that if they used it for medical purposes, that people would freak out about the word nuclear because it has a bad connotation to it. But really what it is a huge magnet. And what it does is look at a structure like this and give you information of what that structure is. So we're going to be mostly focusing on what we call hydrogen NMR. So it's usually abbreviated H-NMR. So it's looking at each one of the hydrogens on this molecule. Another type of NMR that you can have is something called carbon-13 NMR. We are not really going to talk too much about it. It might be mentioned when we do our field trip to North Central College, but really we're going to focus on what they call proton NMR, so hydrogen NMR. So we could take this spectroscopy and we could actually figure out what the structure is. Again, IR has given us functional group, mass spec has given us how big the molecule is. This is going to give us the actual structure. Okay. So this has been available for the last 50 years. So it is, and it is known as NMR. It is the technique used to determine the structure of organic compounds. This is the one that everybody uses. Again, sometimes IR is just kind of off to the side. It used to be the premier one, but now it is NMR. So go down to the second paragraph. The nuclei of many isotopes have a characteristic what we call spin, because what we're going to be doing is putting these molecules into a big, big magnet. So we have what they call integral spins, but what we want to carry focus on is down here, the ones that have a spin of 1/2. And again, I'm going to go, and again, this is for organic chemists. It's used for many different applications, but since we're only focusing on organic in this course, that's why we have it. So just a little background of how this works. If you were to have this on your screen, you would have a spinning charge, and that gives what we call a magnetic moment or magnetic field due to spin. In the presence of then an outside magnet, okay, you get what we call 2 spin states. One is a positive 1/2, one is a negative 1. And so what you will have is this is spinning counterclockwise, this one is spinning clockwise, and you have 2 different what we call spin states. What is interesting about these spin states is the difference in energy between depends on what we call the external field strength. So depending upon the size of the magnet that you have for an NMR, it's going to be different. So if you go to the next page, you will see this little diagram here kind of showing you the difference in energy between what we call the negative and the positive 1/2. So strong magnetic fields are necessary for this spectroscopy. The unit they use is a Tesla. It is not the car we're talking about here. And the spectrophotometers that we're using have between 1 and 20 Teslas in terms of the strength of their magnets. For NMR, the small energy difference is usually given as a frequency unit of megahertz. And so that's going to be what we're seeing. But also, a sample is irradiated with what we call radio energies. Again, this is another part of the electromagnetic spectrum that we kind of discussed before. And then this last part here, for the spin of 1/2, the energy difference between those 2 spins give a magnetic strength proportional to their magnetic moment. So there is a pattern to hydrogens and carbons on how they behave in an external magnet. So again, it's kind of like IR frequency. It always reacts with a carbon molecule. So this is useful to chemists. So again, it is called Proton NMR. So again, abbreviation is HNMR. Okay. So what we have is a setup has what we call a continuous wave. So that means we are hitting it with radio frequency. So this is a basic schematic. Here is your sample tube. And what you're doing is spinning the sample tube, and you are putting it in a very strong magnet. And then you have a way of, and you're hitting it with radio waves, excuse me. And then you have a way to detect what is happening with that sample, okay? All right, so we're gonna flip to this page and go down to the bottom, okay? Why should proton nuclei be different, have a different NMR? So again, the biggest discussion here is, well, hydrogen is hydrogen, right? So if I have hydrogen in one carbon molecule versus another, what's the difference between the two? So with electrons surrounding the proton in a covalent compound, an ion, since these electrons are, of course, charged particles, they move because of what the magnetic field happens to be. So what you have is what they call a generates a field that opposes much stronger. The secondary field shields the nucleus from the applied field, so it must increase in strength. So there is a difference between if a hydrogen is attached to something that has what we call more shielding due to the fact that the electrons are behaving differently in that covalent bond. So in NMR, we are going to be using something called parts per million, ppm, as our unit here. All right, so we are going to be talking about something called chemical shifts, okay? So you need to find your IR table that we talked about before and flip it over to the back side where it has what we call proton NMR shifts, okay? So we are going to be talking about something called a chemical shift, okay? So different from IR and UV vis, okay, where the absorption peak is uniquely located by a frequency or wavelength, the location of the NMR resonance signal depend on both the external magnet and the radio frequency that you're hitting it. So the issue you have with NMR is, and this is what drives students crazy, is there's going to be certain places where certain hydrogens are going to behave in an NMR, but these are not hard, fast rules. So it's not like a C double bond O and an IR is always in the 1700s. Here, things might be different depending upon what the magnetic field is or what the organic molecule happens to be, okay? So, if you would, skip that next page and go to this page here, okay? What this is trying to show you on the top here is the hydrogens that are attached to more electronegative elements are going to be in a different place on the NMR due to the fact that the electrons are going to be pulled in different places depending upon the magnet they are in. So we are going to have what we call different ranges for where these hydrogens are going to show up depending upon what it's attached to. So what you're going to see, kind of like you saw with IR, parts per million are going to be on the x-axis, and it's going to go from right to left. The numbers are going to get bigger. They call this the low field region, high field region. Again, you don't need to worry about that. But what you're going to see is different patterns to what hydrogens are attached to different types of organic functional groups. And that's going to be where they appear on the NMR. So I have this table, which I think is much easier to use than that table there.